So, we looked at multicollinearity, and we looked at, another example of why we might use a grid search and how we could use the bag of words model to actually, make predictions. What I now want to do is revisit this notion of accuracy, which we started using last class to evaluate classifiers, and in particular now let's just think again about binary classification. We've used accuracy as our performance metric, right? We've said one classifier is better than another if it has higher accuracy, okay? The issue, though, is that accuracy treats all correct predictions the same, and it treats all incorrect predictions the same. But this isn't always desirable, right? Let's think about a COVID test, which you can think of as being a binary classifier, right? It either predicts you have COVID and it predicts you don't, right? There are two types of errors that the test could make, right? Either it could say you have COVID when you really don't, or it could say you don't have COVID when you really do. Right? Those are the two types of mistakes it could make. Do we agree? Now, which one of these do you think is probably worse? Yeah. Yeah, saying that you don't have COVID when you really do. Right? They're both probably bad. You probably don't want to quarantine for no reason, but it's probably worse to think you don't have COVID and then go wherever, and then later find out that you actually did and you infected a bunch of people. Right? So these two errors are actually, one is much worse than the other, but accuracy doesn't consider that. It just says you got it wrong or you got it right. Okay, so we need to look a bit deeper than just accuracy if we want to evaluate the quality of our classification. Okay, so here's a motivating example. So I assume you've heard of the fable, The Boy Who Cries Wolf? Okay, if you haven't, essentially there's, this kid, I guess, and his family owns a bunch of sheep, and he gets bored and he's like, there's a wolf coming, and he says that to his family or the town or whoever. And because they think a wolf is coming, they run out of their houses to go and protect the sheep, right? Because the wolf will eat the sheep if no one stops the wolf, right? So he says, hey, there's a wolf. Everyone come save the sheep. But then they come outside to save the sheep, and there's actually no wolf, and they're like, stupid kid, right? And so he keeps doing this. He keeps saying, there's a wolf. They all run outside to save the sheep. Turns out to be no wolf. Okay, so after a while, they learn that the kid is just playing jokes on them. Right? So they stop trusting the kid. But then one day there's actually a wolf. And so again, the kid is like, there's a wolf coming, like I'm being legit this time. There's actually a wolf. But they stop believing him because he lied so many times. And then the wolf comes, and the story says it turned the sheep into lamb chops. Very graphic. Okay? And so, firstly, are we comfortable with what the story is talking about? Right? Every time this kid said anything, he said there's a wolf. There are two possibilities after that, right? There was a wolf and there were no. He said there was a wolf and there were actually no wolves. And then at the end, he said there was a wolf and there was a wolf. Do we agree? Okay. So in the context of binary classification, we think of predictions as being either positive or negative. You can think of positive as meaning like 1 or yes, like someone has COVID or something like that, and negative as being no or 0. Okay, so here, a positive prediction is the kid saying, there's a wolf. And a negative prediction is the kid saying, there's no wolf. Even though it's probably emotionally positive if there's no wolf, but that's not what this is thinking about. Okay, positive equals wolf, negative no wolf. All right. So what's an example of an incorrect positive prediction? What does that mean in the context of the story? Yeah. But what did the kid say? Right. So a positive prediction is one where he says there's a wolf. Okay? For it to be incorrect, there should have been no wolf. And that's what happened for most of the story. He kept saying there's a wolf, but there actually wasn't. Okay? And so that's what's known as a false positive. You say it's positive, or you classify it as being positive, but it's actually not. Was there an instance of a correct negative prediction? You're nodding yes. What was the correct negative prediction? Well, so, note that the kid only ever said one thing. He only said there's a wolf. And so his prediction was always positive. It wasn't always right. Every single time the kid said something, he only ever said one thing. He said, there's a wolf. No worries, no worries. And so he always made positive predictions. So there is no correct negative prediction because there is no negative prediction at all. Do we agree with that? He's only saying wolf, wolf, wolf. But a negative prediction would be him saying no wolf. And that never happened. Do we agree? Okay. So, notice there are 4 possibilities for what could happen, right? Either the kid could be right or wrong, and there could be a wolf and there could not be a wolf, right? So there's 4 possibilities as to, how this prediction can turn out. And those are summarized in this table, which is often called a confusion matrix. It's not called confusion matrix because you're confused when looking at it. I don't actually know why it's called confusion matrix. Okay, so let's think about the 4 outcomes here. Right, remember, a positive prediction is one where the kid says there's a wolf. A true positive prediction is one where his prediction was true. He was correct. So if he says there is a wolf, and there actually is a wolf, that is a true positive. Do we agree? And so that's what we were seeing in the top left. Ideally, people believe him. Like, that's a separate issue. People weren't believing his predictions. But a true positive would be him saying there's a wolf, and there actually is a wolf. And the consequence of that would be they get to save the sheep in time, right? Because they know the wolf is coming, they can save the sheep. Remember, a positive prediction is him saying there is a wolf. A false positive prediction is when he says there's a wolf, but there isn't actually a wolf. And this is what we saw for most of the story, right? And this is in the top right. He kept saying there's a wolf, but there wasn't actually a wolf. And so the consequence of that was that his family and the other people in the town, just got angry at him for, waking them up because he wanted to play games with them. Okay, so a false positive here was him saying there's a wolf when there wasn't actually. Do we agree? Okay. Well, then let's look at negative predictions, which remember the kid did not make. So these bottom 2 scenarios didn't happen. Do we agree? Right? It turned out the wolf did eat all the sheep, which is what the bottom left is saying, but it's not because the kid said there was no wolves. It's because the town stopped believing the kid, right? Which is like a level of nuance that this picture does not capture. Okay? But remember, a negative prediction is one where the kid says there is no wolf. And so, like a positive prediction, a negative prediction can either be right or wrong. So a true negative prediction is one where you predict that there's no wolf and you're correct. Okay? And so if you predict there's no wolf and there is actually no wolf, well then, that's good because you were right about the fact that there is no wolf, but it's uneventful, right? Because nothing really happened. Okay? Notice this didn't happen in the story because the kid never said there's no wolf. He always said wolf is coming. A false negative is the worst possible outcome here. It's when you say there's no wolf, but there actually was. That's the false part. Right? It's negative because you're saying there's no wolf. It's false because you're wrong. And this would happen if you said there's no wolf, but there actually was, and what would happen then is no one saves the sheep and they get turned into lamb chops. Right? So the 2 types of errors here, false positives and false negatives, while they are both mistakes that the classifier made, in different scenarios, you might think one type of error is more important than the other. Right here, I'm sure the people would be okay with being woken up if it meant the sheep not getting turned into lamb chops. We agree? Okay. So, we just discussed what a true positive, false positive, true negative, and false negative is. And this new structure we defined was called a confusion matrix. Now, to add to the confusion you may have when looking at a confusion matrix, different websites format confusion matrices differently. So if you look back here, here are the columns, like this was the actually positive column, this was the actually negative column. Do we agree? Right? Actually, an easier way to look at it is this was the row where you predicted positive, because they both end in P, and here's the row where you predicted negative. So that's how this confusion matrix is set up. But a more common configuration, at least in scikit-learn, is that your predictions are in the columns. Okay, it doesn't really matter mathematically. You just need to keep track of where, like how it's organized so that you know how to interpret the numbers. Okay, so here I have a predicted positive column and a predicted negative column. I have an actually negative row and an actually positive row. I've set it up this way because this is how scikit-learn does it. Okay? So for all 4 possibilities, we have like one count, right? So true positive and true negatives, that's what we want. That's when our classifier is correct. False positive and false negative, that's when our classifier is wrong, right? And remember, the way to interpret these 4 acronyms is that the first letter, true or false, tells you whether or not the prediction was right, and the second letter, negative or positive, tells you what you predicted. So false positive means you were wrong and you predicted positive. So it actually should have been negative. Do we agree? Okay, so any questions with the confusion matrix we see here? Sound okay? All right. So let's look at an example here. Here, let's just suppose UCSD administers hundreds of COVID tests a day. And as we know, COVID tests are not 100% accurate, so there are some types of errors. And let's suppose each test is either positive, meaning the prediction is that the patient has COVID, or negative, meaning that the prediction is that the patient doesn't have COVID. Okay? What's a true positive in this scenario? Yeah. Right, a true positive is the scenario where you have COVID and the test says you have COVID. We agree? All right. What's a false positive? Yeah. Right. A false positive is where the test says you have it, but you actually don't. It's like a false alarm. Right? You rang the fire alarm, but there isn't actually a fire. Okay? A true negative is probably the case that we're hoping for. It's when it says you don't have COVID and you don't actually have COVID. We agree? And then what's a false negative? Yeah. Yeah, so the false negative is probably the thing we, are most trying to avoid. Right? We really don't want this scenario where it says you don't have COVID, that's the negative part, but you actually do, and that's the false part. Okay, so are we comfortable with what all 4 of these terms mean? Okay. So let's pretend we somehow have access to the results of UCSD Health's COVID tests. Note that in practice, it might be hard to actually collect this data because we would need to know if someone actually has COVID. But to do that, you would need to take a test, and the test has error. Right? But let's just suppose we somehow are able to see whether or not you truly have COVID in your body. Okay? And here are the results summarized in a confusion matrix. What is the accuracy of these tests combined? What is the accuracy? Yeah, right. Remember, the accuracy is the proportion of times the test was correct. Right? It was correct when we have a true positive or when we have a true negative. So we're looking at the diagonal here. 1 plus 90, that's the numerator. In total, there were 100 tests, which I could get by adding up all 4 numbers in the grid. And so that gets me 91%. Comfortable with that? Okay. So, we may see this and say, hey, the COVID test is 91% accurate. That's not, that's pretty good. But what would happen here if we said, okay, let's just ignore what the test says. What if we just predicted that nobody has COVID? So we take, we swab someone's nose and we throw it away and say you don't have COVID. What would the accuracy of that test be? If we just say no one has COVID, why would that be 91%? Exactly. Here, if we just said nobody has COVID, then we only have to look at one column, right? Everyone's either a true negative or a false negative. How many people actually don't have COVID? 91, right? Because this is the actually negative row. 90 people here don't have COVID, and then one more person here doesn't have COVID. So 91 people don't have COVID. So if I just say nobody has COVID, then 91% of the time I am correct. Do we agree? I don't need to know any science or biology or swab anyone to do that. I can make a 91% accurate test just by saying no one has COVID. Do we agree with that idea? All right. And so hopefully this illustrates the fact that just looking at accuracy doesn't tell you that much, especially in cases like these where there is significant class imbalance. And what that means here is that there are way more negative people, negative COVID-wise that is, than positive people in our data set. Right? So if I just predict the most dominant class, my accuracy will be really high. Do we agree? And so just looking at accuracy, doesn't tell us a whole lot. And so instead, we have these alternative metrics that look at the types of errors we are actually interested in here. Right? If we look at the bottom row, what we have highlighted is all of the people that actually have COVID. And I would argue when running a COVID test, what is most important is that you identify the people who have COVID. Do you agree? Okay? And so if I look at this bottom row that I've highlighted, what proportion of people who actually have COVID did the test correctly classify? Yeah. Yeah, it's 1 out of 9. Right? Of the 9 people who actually have COVID, so these 8 plus this 1, only 1 of them did the test correctly classify. Right? So even though its accuracy was 91%, it only correctly identified 1 of the 9 COVID cases, which means it's actually pretty lousy. And so the calculation we just did is what's known as recall. Okay? So the recall of a binary classifier is the proportion of actually positive data points that are correctly classified. And so recall is important in cases like a medical exam, where you want to make sure that you identify everyone that has a disease or everyone that has COVID or what other condition, right? And so here, the classifier had high accuracy but low recall, which means it's not that great in identifying COVID.